All right, so I'm going to list some quantities that you'll study in this in this course. Okay.
Nothing's sticking.
Okay, so you'll just have to let me know. Okay. All right, so I got two sets of quantities that you'll learn about sometime during this course. Okay. Do you see any difference between the two classifications?
One has to do with movement.
Okay. All right, what is velocity? Okay, velocity. Yeah, go ahead.
I was going to say, is it the amount of energy that something carries while it's moving?
Okay, velocity is a quantity that tells you how fast you're moving and in what direction you're moving. What is speed?
How fast?
Speed just tells you how fast you're moving. It doesn't give you a direction. Okay? Pressure, it's just one number. It tells you what is the magnitude of the pressure. Temperature is just one number. Okay? So what these quantities are called scalars. All you need is one number to specify them. Okay? So these guys are scalars. Okay? All these quantities have magnitude to them and direction to them. Okay? So you need more than one number to specify them. Okay? And these quantities are represented by vectors. Okay? How many numbers do you need to specify them? I'm sorry? So in 2 dimensions, you need 2 numbers to specify them. In 3 dimensions, you need 3 numbers to specify them. Okay, why do you need 3 numbers in 3 dimensions? One for the magnitude, and 2 numbers for directions. Okay, so let me show you an example. All right, so here is an axis, and here is a vector. Vectors are denoted by line segments. The length of the vector gives you the magnitude. So the convention would be, so let's say you're going at 50 miles an hour in this direction. How would you draw 100 miles an hour in that direction? No, double. Very simple. Okay, so we use this to specify the vector. Okay, so here are the 2 angles that you need to specify this vector. Okay, so the convention, there's various ways to do it. So here's one angle to specify it, and then you project it on the XY plane, and here's another angle that you specify. All right, so what we are saying is, to specify this vector, you give its length, and if you give me these 2 angles, I know exactly what vector you're talking about. Okay. So to specify this vector, we'll call this, and the notation for vectors is you use a capital letter with an arrow on top, or a small letter, it doesn't matter. Okay. So the magnitude is A, theta, and phi. So if you give me these three numbers, you specified that vector for me. All right. So we'll be studying many quantities that are specified by vectors, by a mathematical quantity called vectors. Okay. So in 2 dimensions, you need 2 numbers. In 3 dimensions, you need 3 numbers. In n dimensions, you need n numbers to specify a vector. 1 for the magnitude and n minus 1 numbers for the direction. All right. When you first learn about numbers, how do you get to know numbers? When you learned 1, 2, 3, 4, 5, the first thing you learned to do was to add them, subtract them, multiply them. That's what we're going to learn this chapter. Okay? So vectors is a new kind of quantity, and all this chapter is about is learning to add vectors, subtract vectors, and multiply vectors. All right, so let me show you. So okay, so that's what this chapter is about. Yeah. So here is a vector A, and here is a vector B. Okay. Now here's the rule for this for vectors. Okay. Here's this vector B. Okay. This vector is parallel to this vector. It is the same length as that vector, and those two vectors are equal. Okay? So that's all that matters. It doesn't matter where you draw it. So for instance, a physical example of this is, let's say you're driving north on Nova Road at 50 miles an hour, or you're driving north on 95 at 50 miles an hour. Your velocities are the same. Okay? So two vectors are equal as long as their lengths are the same and they're pointing in the same direction. All right, so what I'm going to show you is how to add two vectors. Okay, so here's the vector A, and what we'll do is we'll take this vector, bring the tail of that vector over here. Okay. And here's the sum of the two vectors. That's how you add two vectors. Yeah, very easy. All right. Now, if I show you how to add two vectors, can you add three vectors? Do you know how to add three vectors? Any guesses on how you would add three vectors?
Make it a different shape, or make it 3D.
Add the third one to the tail of the second one.
Very good, my friend. There you go. See, that's the nice thing about science. It's very logical. Okay? Once you there's A plus B plus C. All right? Now, how many vectors could you add together? There you go. So you just learned how to add any number of vectors, okay? Just like you know how to add infinite number of numbers, okay? And you're learning that in your calculus classes. You're learning how to add series sums and stuff like that. Okay, so now we know how to add vectors. Now let's learn how to subtract vectors, okay?
I have a question. You
Yeah.
said that if you have a duplicate B, just in like another row, for example, that they'd be equal. Does that mean that they have to be the same direction though?
Yeah, they have to have the same magnitude and same direction. Yeah. All right, now to subtract vectors, so let's say A, here's B, okay. And if somebody asked you to subtract vectors, what you have to realize is, all you have to do is do one more definition. Subtraction is really addition of negative of B. So if you define negative of B, then you know how to do subtract two vectors. Okay. What do you think negative of B is? And there you go. All right. See, I'm getting paid for telling you all stuff that you already know. Okay, this is a good gig. All right. So A minus B is, there is A, there is minus B, and there is A minus B. All right, so in 5 minutes, we've learned how to add vectors. So what are we doing here today? We are learning a new mathematical quantity. And the way to get familiar with new mathematical quantities is to learn how to add, subtract, and multiply them. Okay? You will learn about matrices. That's what you'll first do. You'll learn how to add matrices, subtract matrices, and stuff like that. Now we'll learn how to multiply vectors. Okay? Now multiplying vectors is a little more complicated. Okay? So we'll need some tools to be able to multiply vectors. Okay? But I'll tell you that there are two kinds of products. Okay? When you were multiplying numbers, okay, numbers were simple beasts, and there's only one product. 4 times 5 is 20, and 5 times 4 was also 20. Okay? So you learn that when you multiply vectors, there's two kinds of products. There's something called a dot product or a scalar product. Okay? And this product behaves like multiplying numbers. Okay, so this product is just like this, is commutative under multiplication. Okay. There's another product called the cross product. Now this guy is minus B cross A. So you see, this is different than multiplying numbers. Yep. So when you multiply vectors, there's two ways of multiplying vectors. Here's one way of multiplying vectors, and here's another way of multiplying vectors. Okay.
You said the first one's called dot product?
This is called a dot product because of the notation. Okay. And also the answer is different. For this guy, the answer is a scalar. So it's also known as a scalar product. The answer here is a vector. Okay, so we'll give you the details of that once we have all the tools to give you the details. Okay? All right, so everybody understand this? What are we doing here today? We're learning about vectors. We'll learn how to add, subtract, and multiply them. All right. All right, so let's get into the slides, and I'll go fairly quickly. Okay. So vectors, scalars are quantities that have magnitude and no direction. Okay. So we saw examples where pressure, temperature, speed, and so on. Vectors have both magnitude and direction. Okay. So velocity, force, momentum, acceleration. Okay. And how many numbers do you need to specify vectors? N numbers in n dimensions. Okay. Here's the notation for vectors. This tells you the magnitude of the vector, and this is also the magnitude of the vector. Okay. Or if it's bold, that's a vector. Okay. So here's a vector, here's a vector, here's a... Okay. By the way, this is sort of implied and unsaid, but when you add apples to oranges? No. So when we are adding vectors, it's understood that if this is a velocity vector, that is also a velocity vector. If this is a velocity vector, that can't be a force vector. You wouldn't add those two. Okay. All right. All right. So here are vectors. Okay. Here the first physical vector will define something called the displacement vector. All right. So let's say you go for a walk. You start off here and you end up there. Okay. The displacement vector is a vector that points from the starting point to the end point. That is the displacement vector. And so you see, you could walk along this path or this path. Your displacement vector is the same. Okay. So your displacement vector is a vector pointing from the starting point to the end point. Here's a vector A. You guys understand what 2A means? 2A just means a vector twice as long. Okay. Now here's something that hidden that we slipped under you. Okay, what we have done here is actually, see, A is a vector, 2 is a scalar. We multiplied a scalar to a vector, but you intuitively knew what that meant. What is minus 2A? Twice as long in the opposite direction. Okay. What is half A? Half as long. Okay. Mm-hmm. All right, so these two vectors are equal. You see, they have the same magnitude and same direction. And so you already saw how to add vectors. Here's a vector A and B. And remember, you can move this vector to any location as long as you're moving parallel to it. It's pointing in the same direction and you don't change the magnitude. All right, now here's another thing that we didn't tell you, but this is assumed. Okay, so this is in Euclidean geometry. So you can think of, if you're doing 2 dimensions, this is in a plane. It's not on the surface of a basketball or an orange. Okay? All right, so you can move this parallel to itself. So here's A, there's B, and there's A plus B. So here's, you know how to add 5 vectors or an infinite number of vectors. There's the sum. Okay, so here's what we're going to do. We're going to test all the properties that numbers obey. We're going to test them on the vectors. Okay? You knew how to add a bunch of numbers, so we're learning how to add a bunch of vectors. Okay. Now, about numbers, you know that 4 plus 5 is equal to 5 plus 4. You want to know if that's true for vectors. And it turns out that it is true. So, and the technical term for that is commutative law under addition. Okay. So here is in diagrams, here is A plus B, and this is B plus A. And the answer is the same. Okay. So this is the property we are verifying. Okay. So in fact, you could generalize this to any number of vectors. You can reorder them any which way you like, and the sum will be the same. So here it is. With 3 vectors, you can add them in any order. You can add B and C first, and then add A, or A and B, and then add that to C. The final answer will always be the same. Okay? So here's A plus B plus C, and this is just showing you in diagrams this. Yep.
So regardless of any sum of any vectors, the displacement vector will always just be the shortest distance from A to the last one.
Yeah, this displacement vector is, yeah. Yeah, you start off here, go there, you go to Mars and come back, same displacement vector. You already know how to subtract vectors, okay? Subtracting vectors is really about defining what the negative of a vector means, and then you're just adding the negative of the vector. Okay? So B is that vector, the negative B is that one. Scalar multiplication, what does that mean? You're multiplying a vector by a scalar. Okay? So here's the vector, here's the scalar. Okay, so here's the vector, and here is the scalar. So 3A is just a vector 3 times as long. Okay, now we're going to build the tools for learning how to multiply vectors. Okay? All right, so you have to keep this in mind. So a velocity vector, the dimensions of the velocity vector are meters, length over time, meters per second would be the units. Acceleration vector, the units would be? I'm sorry? Yep. Force would be newtons, kg, meters per second square. Momentum would be kg, meters per second, and so on. Okay, so they have all different dimensions. All right, so it's useful to define vectors that are dimensionless.
There we are.
Yeah. So I've learned the trick now. I just have to change the page. So it, for some reason, it goes to sleep, I think.
Well, it still shows like the laser point and everything that you're writing currently.
Mhm.
But the moment you lift the pencil, it just fades out.
Okay. All right, so we'll introduce 3 special friends. Okay. These are unit vectors. Okay, what do you think that means?
Multiply them by a unit.
Their length is 1 unit. Okay. And they're dimensionless. So we're going to use them for velocity, acceleration, and so on. Okay? So these are unit vectors and dimensionless. I points along the x-axis of unit length, j along the y-axis, k along the z-axis. Okay, so and you want to get used to various notations. Some books use this z hat. I like to use I, j, and k. Okay. And this is a right-handed coordinate system. Okay, so here is a right-handed coordinate system. This is a left-handed coordinate system. All your textbooks, everything, everywhere in the world, we use right-handed coordinate system. So we've beaten every scientist to use right-handed coordinate system. Okay? And here's what this means. If you turn, this is the x-axis, y-axis, z-axis. If you turn a screw from the x to y-axis, which way will the screw move? Toward the z-axis. Okay? So there's the right-handed coordinate system. All right, so those are unit vectors I, j, and k. All right, so now let me so let's work through something. What is this?
Two-dimensional plane,
Is it a scalar or a vector?
scalar.
It's a vector. It's the unit vector I.
It's just hard to read what that says.
Yeah.
Oh,
That's what we're starting with.
you're making fun of my handwriting, huh? You just, what's that?
You'll be able to make fun of
Yeah.
everybody's eventually.
That's okay, he just blew his A. No, I'm just kidding. All right. So what is that? A vector. What is this? No, what is this guy?
It's a
Vector?
It's a vector.
vector, but like back and forth.
So there is I hat, and there is 5i. Okay. What happened? Did I scare you?
Oh, no, I'm terrified, yeah.
All right. What is this guy? Vector. How about this guy? That's a vector as well, 7j. And now let's add these two guys. You already know how to add them, okay? So you see, this is 5i. Oops. This is 5i, and I'll draw 7j. And there's this vector. Let's call it A. Okay, writing vectors in component form like this is useful for multiplying, adding, and subtracting. Okay, so I showed you a whole bunch of drawings how to add and subtract vectors, but that's not a practical way of doing it. In practice, if you want to add, subtract, and multiply vectors, you need to write vectors in this form. Okay? So now let me give you another vector. B equal to 3i plus 8j. So A plus B is, you just add the corresponding components. I'm sorry? Very good. See, I didn't even have to tell you. That's how easy it is. Okay?
I think with the, I'm not sure what it's called, but the little symbol above the letters is, you kind of do the interchangeably.
Yeah. Here I was not lazy, here I was lazy.
So I should write the symbol.
doesn't matter. I'll know. Yeah. I don't know how to do A minus B. You guys want to help me? Two I minus j. Okay? All right. So you know how to add and subtract vectors. All right. So the rule is the following. This is called the x component of A. This is called the y component of A. All right. So remember, if you have two vectors that are collinear, then if this is 2 units and that's 3 units, that's 5 units. So you can think of this as, well, these are collinear vectors. Okay, so you just add the components. Or you can think of this as 5x plus 6x, and add the 2. So this would be ax plus bx I So that's how you add vectors. You just add the components. In fact, now you can do all kinds of complicated operations. Okay, so let me ask you, what is 3a minus 4b? Any guesses on what that might be? Okay. So you see, once you have a vector in component form, then you can do algebra very easily. Okay. All right. So here, and I'm showing this for 2 dimensions. You can generalize this for 3 dimensions, and so on. But this part works only in 2 dimensions. Okay, so this is the x component and the y component. Okay, so in 2 dimensions, there's a vector. How many numbers do you need to specify the vector? 2. Okay, so here are the 2. In 2 dimensions, you can give me the magnitude and the angle. And the angle is, angle conventionally is measured counterclockwise from the x-axis. Okay, so if you give me the length of this vector and this angle, then you've completely specified the vector. Or you can give me this number and this number. Or you could give me this number and this number. And you completely specify the vector. Okay. So you could give me this set or this set. Which set has more information? They have equal information. Okay. Or you could give me ax, or you could give me theta ay, or you could give me ay, any combination of 2 numbers. You completely specify. Okay. The polite thing to do is either give this set or this set. You give these numbers if you want to mess with somebody. Okay. All right. So anyway, you need 2 numbers to specify a vector in 2 dimensions. Okay. All right. So this is the magnitude and direction, and these are the components, x and y components. All right, so oftentimes you'll be given this set or that set, and what you'll need to do is you'll need to find the other set. So if you're given this set of numbers, you'll need to find that, or if you're given this set of numbers, you'll need to find that. Okay? So if you're given this set, the magnitude and direction, okay, and again, this is measured counterclockwise from the x-axis. If you want to find the components, ax is a cosine theta, and ay is a sine theta. Okay, so these formulas let you go from here to there. And if you're given this set of numbers and you need to go there, then you use these formulas. Use the components, and there is the magnitude. The angle theta is tan inverse of ay over ax. Okay. Now you'll learn that this inverse function has two solutions, theta and theta 1 plus 180 degrees, but we'll come to that later.
It's not as scary as that one.
All right. So here's a vector. Okay. Now we'll tell you if both the components are positive, x and y, then the vector is in the first quadrant. If this component is negative and that's positive, then the vector is in the second quadrant. If both components are negative, then the vector is in the third quadrant. If this guy is positive and that guy is negative, the vector is in the fourth quadrant. So you learned how to add vectors. This is the diagram. This is a diagrammatic way of adding vectors. This is a good picture to have in mind, but this is not a practical way of adding vectors. The practical way of adding vectors is using components. Okay. So if you wanted to add two vectors, you write the components of the vectors, and the x component of the resultant is sum of the components, and the y component is the sum of the y components. Okay. See, these are collinear vectors, and so it's ax plus bxi. All right, so in physics, we write our laws as equations. Okay, and you learned that in an equation, if you have apples on the left-hand side, what is it that you want on the right-hand side? Apples. Okay. So here's a vector on the left-hand side. On the right-hand side, you have a sum of three terms, but each one had better be a vector because you want a vector on the right-hand side. Okay. That's a vector. That's a scalar times a vector. That's a vector. That's a vector. Scalar, scalar times a vector, a vector. Okay. So what this equation is telling you is that this vector is equal to the sum of these three vectors. What else do you want? Okay, this is a vector. The right-hand side is a vector. Okay, so this is a position vector, and the units would be meters. So the dimensions of each of those must be meters as well. Length as well. Okay, this is a position vector, length. This is length over time times time, gives you length. This is acceleration is length over time square times time square gives you length. Okay. So it has all the right qualities. Okay. All right. So whenever you have an equation, if you have a number on the left-hand side, you have to have numbers on the right-hand side. If you have vectors on the left-hand side, you have to have vectors on the right-hand side. This is a 4x4 matrix. Okay. You guys have seen matrices? So this guy is something like that. This guy is a 4x4 matrix. Scalar times that is a 4x4 matrix. This guy is a 4x4 matrix. This is what Einstein is famous for. Yep. This is Einstein's general theory of relativity. See, about 16 symbols, and we're talking about him 100 years later. Okay, what this tells you, what this equation tells you is, so Einstein tells you, if there is no matter and energy, space-time is flat. Okay. If you put matter in space, it'll curve. The space-time curve. So this stuff on the right is about the matter and energy distribution. And this equation is telling you matter and energy is telling you how for the space-time to curve, how the space-time curves. Okay. So that equation is telling you so you see, this matter distribution curved space-time. Okay. And here's the funny thing, I guess. So this is flat, right? If I roll this marble, how does it move? In what direction does it move? Straight line. This guy is moving in a straight line. Okay, so what does the straight line mean? The straight line means, what does the straight line mean?
Shortest distance between 2 points.
Very good. Okay, so if you calculated the distance along this path, that path is the shortest distance, and I'll tell you how to calculate the distance in a second. If you calculated the distance along that path, that's a greater distance. Okay? So, what Einstein says is, matter and energy tells space-time how to curve, and if you're small enough where you're not affecting space-time, all you're doing is moving in straight lines when you go from point A to B. So the Earth is going around in a straight line. Okay. Well, how do we measure straight lines? And what is the definition of distance measurement in? Okay. So again, I'm just going on a tangent here, but hey, what the heck, you know? Okay. So here's how you measure distance. Okay, so here's the distance between 2 points. Okay, so x, y, Okay, so dt is t2 minus t1. So these are infinitesimally separated points. Okay, and so on. So going back to here. So here's what this would mean. So you are here now. Oops. You are here now, and half a second later you were there. So dt would be half a second, dx would be the distance between those 2 points, and so on. Okay. And here's how you calculate the distance using this formula. Okay, so along that path, if you add up all the sum up all the different distances, like I said again, okay, if you sum up all the distances along that path, that's the shortest distance between those 2 points. Okay, so this was Einstein's equation, and like I said, this tells you how
One way again.
energy and matter is distributed. I'm sorry.
One way again.
Yeah. This tells you how matter and energy is distributed, and matter and energy tells you how space-time is curved. Yeah. So, now that we are on a tangent, we might as well stay on a tangent. All right, so let's say I have a rock that I've tied to a string. I'm whirling it around. What happens if the string breaks?
The rock goes away in a line tangent to its orbit.
Very good. Okay. And when does it go in a straight line?
As soon as you let it go.
As soon as you cut the string.
Yeah.
Okay. Everybody understand that? All right, so we'll do the following experiment. The Earth is going around the sun. We'll flip a switch and make the sun vanish. Have you done that before?
Once or twice.
Huh?
Once or twice.
Okay, so we'll do it again. What will happen?
The Earth will just start moving in a straight line.
Soon as you flip the switch?
9 minutes after.
8 minutes after. Why 8 minutes after?
Because that's how long it will take the gravitational force to get from the sun to the Earth.
So, all very good answers. So here's what's happening. Okay. So here was this sun that curved the space-time. When you make the sun vanish, now you've removed this matter and energy. It takes, the space-time is becoming flat, and by the time it becomes flat near Earth, that is happening at the speed of light. It takes 8 minutes to happen. Yep.
So if that movement is just the folding of space-time, why does that travel at the speed of light?
I'm sorry?
Why does the folding of space-time travel at the speed of light?
Why does light travel at the speed of light? That's what we've observed. Physics is about describing nature. That's what.
But if it's based off gravity, doesn't gravity? Well, I guess is it because it doesn't exist in a vacuum, or does it not matter? Is it just because it just is? Because of what gives the gravitational?
No, so gravity, what we are saying is, okay, so Newton said that this guy attracts this guy. Now this is a force at a distance. How does that happen? I mean, you didn't question that. Einstein is telling you that, okay, this guy is curving space-time. This guy only is responding to his local environment. Again, that makes more sense. You're responding to what's next to you. Okay. This guy doesn't care how the space-time was curved. He's just going he's going on a path that is what is available to him. All right, so let's do products now. Okay, so we'll learn the first way of multiplying vectors, A dot B. So here's the notation for it. It's called dot because of this dot written in between. And it's also called a scalar product because the answer is a scalar. And this product has this property like the numbers. 4 times 5 is the same as 5 times 4. So this product has the same, is commutative under multiplication, okay? And here's the definition, okay? So vector A is AXI plus AYJ plus AZK. Okay, so we are doing three-dimensional vectors, and similarly B is BXI, BYJ, and so on. Okay, so A dot B is defined as AXBX plus AYBY plus AZBZ. That's the definition. Okay, this is a scalar, scalar, a scalar. Sum of three scalars is a scalar. Okay. Here's A dot B defined in terms of the length. If you draw A and B from the same point and phi is the angle between them, A dot B is equal to the length of A times the length of B times cosine of the angle between them. So this is equal to that. Okay, so this is the scalar product, and this product behaves, is commutative. So that's, okay. So here's a way of multiplying two vectors. Okay, you're taking two complicated objects and coming out, so you're taking two vectors which are complicated objects, and the answer is a scalar. And the product is a simpler object. Okay, it turns out that you will see this formula in work done. When a force acts through that displacement, F dot R is the work done by that force. Okay. You will see that the power is, if you're pushing an object, if you're pushing a car and the car is moving at a velocity v, the force dotted with the velocity vector is the power. Okay, how much energy you're spending per unit time. Okay. So you'll see that in several places, the dot product. Here's the other product, vector product. Why do you think this is named as vector product? Very good, my friend. The result is a vector. Okay. All right. And it's also called a cross product because of the notation. So A cross B, there's the result. C, it's a vector. And here's C. So we're just giving you, here's the definition of C. Okay. If you guys have done determinants, okay, it's that. And it's this determinant, and you have to expand the determinants in terms of that. Okay. All right, so it's C is that. And this product, this vector product is anti-commutative. A cross B is not equal to B cross A. It's minus B cross A. So this product is different than this thing, okay? So the cross product is like that, okay? You just have to remember that formula. And actually, you know, if you do it enough times, you'll naturally remember it. And let me show you how to do this. All right, so C the x component of C, here's how you write it. The x component of C is AY BZ, AY BZ minus the flipped AZ BY. The x component of the product will not have the x components of the two elements, okay? Plus the y component of C, the y component of C is AZ BX minus the flipped AX BZ. Again, it might seem complicated. Again, you'll be surprised. By Wednesday, you'll be an expert on this thing. Kth component. Anybody want to try it? Very good. Minus. Very good. Okay. So that's the cross product. Okay, so that was the second product. The result was a vector, and it's not commutative. It's anti-commutative. All right, so what have we learned in whole R? We've learned how to add, subtract, and multiply vectors. Okay. So the cross product is anti-commutative. The magnitude of A cross B is this. It's A, magnitude of A, times magnitude of B, times sine of the angle between the two vectors. All right, so now let me ask you a question that will, so here is A and a vector B that's parallel to A. What is the cross product of A cross B? Look at the magnitude formula. What is the angle between the two vectors? 0. Sine 0 is 0. Magnitude is 0. So the cross product of two parallel vectors is 0. The cross product of two anti-parallel vectors, that would be sine 180, which would be 0, is 0 as well. Okay? Now, so from this formula, you can't tell. From this formula, it's hard to tell. But here is the rule. So you want to remember this. If this vector is A, that vector is B, there is the vector C. The vector C is perpendicular to the plane containing A and B. And you use your right hand to figure out the direction of C. And you want to remember this because, and let me show you an easy way to do this. All right, so if you want to find A cross B, okay, there's A, there's B, A cross B, here's A, B. If you turn A to B, if you turn a screw from A to B, which way would the screw move? If I turn the screw this way, it'll move that way. That's the direction of C. Okay? The cross product is perpendicular to this plane. So you have to figure out if it's in that direction or this direction. A cross B, it's in that direction. If this was A, that's B, C is in that direction. Okay. If this was A and that's B, C is in that direction. Okay. So if you turn a screw from here to there, the screw would move in that direction, and that's the direction of the cross product. Okay. So you have to, this shows you the special products. Um, I cross J is K, so you have to, I cross J is K, J cross K is I, K cross I is J, okay? And of course, J cross I would be minus K and so on. Okay? So these are special cross products you have to remember. All right, that finishes this lecture.